All right, so example, derivative of numerical values. Just want to look something similar to an example you're going to see. So let y, which is equal to u times v, be the product of u and v of differentiable functions. U and v. If u of 2 is equal to 3, u prime of 2 is equal to negative 4, v of 2 is equal to 1, and v prime of 2 is equal to 2, determine the value of y prime of 2. Okay, so what we know, our solution here. What we know is y is equal to u times v, right? It's the product of two functions. Therefore, y prime is going to be equal to the derivative of the first times the second plus the first times the derivative of the second. So that means y prime of 2 is going to be equal to the derivative of the first at 2 times the second at 2 plus the first at 2 times the derivative of the second at 2. So then when we just plug these numbers in, u prime of 2 we have right here, this is negative 4. And v of 2 is going to be 1 plus u of 2, which is going to be 3, times v prime of 2, which is equal to 2. So really this is just an application of the product rule. So this is going to be equal to minus 4 plus 6, which is equal to 2. Quotient rule. The quotient. So if u and v are differentiable, then u divided by v is differentiable. I should say at its domain. It should be a little disclaimer there because we have v in the bottom and we know that's a problem. But we will, okay, so this is differentiable. Except possibly where v of x is equal to 0, but whatever. So is differentiable. And the rule for this, the derivative with respect to x of u divided by v is equal to it's du dx times v minus u times dv dx all over v squared. Now, my preference is to use f's and g's. So we can say, or, so u is f and v is g. Or if I say the derivative with respect to x of f divided by g is going to be equal to f prime of x times g of x minus f of x times g prime of x all over all over g of x squared. I prefer it to look like that. It's just my my preference, but it is what it is. So we're really just going to kind of shorthand this notation: f prime g minus f g prime all over g squared. Okay, we're just going to start shorthanding these things. So just using these. Now, what I like about me reordering the product rule is, notice you still have derivative of the first times the second, first times the derivative of the second. That the numerator has the same order as the product rule, except instead of having an addition sign, you have a subtraction sign. Just don't forget to divide by g squared. Remember, this is rational, so this has rational form as well. So an example, determine the derivative. So if y is equal to x squared minus 1 all over x squared plus 1. So what I'm going to do is I'm going to label these things. The numerator is going to be f, and the denominator is going to be g. This is going to be g. So what we have is we have the form f divided by g. So that means y prime is going to be equal to f prime g minus f g prime all over g squared. So this is equal to, well, what's the derivative of x squared minus 1? Well, the derivative of x squared, bring the 2 out front, is 2x. The derivative of negative 1 is 0, because this thing would just be a horizontal line. So that's f. Times g, which is going to be x squared plus 1, so that's f prime g, minus, don't forget the minus sign, f, which is the numerator, this is going to be x squared minus 1, times the derivative of the denominator, which is going to be 2x, all over the denominator squared. Now be careful, x squared plus 1 is, don't just square those two terms. You would have to FOIL it if you did want to expand it, but in general we don't really multiply denominators. We like them better in factored form. They're more useful that way. So my recommendation is leave your denominators alone if they're already factored. Now we're just going to distribute because sometimes these things simplify. So the numerator I will always simplify. 2x cubed plus 2x, so boom, boom. Minus, be careful here because you're welcome to multiply these things, but remember the subtraction is going to also change their sign. So this and this, you're going to have a 2x cubed minus 2x. But when you send that negative through, those signs are going to change. So you're welcome to skip this step as long as you understand that. So this is going to be equal to, let me go right over here for a little room. I have 2x cubed plus 2x minus 2x cubed plus 2x all over x squared plus 1 squared. So changing those two signs so we can see that these two will cancel. And then this is going to be 2x minus a negative 2x. So 2x plus 2x is going to give us 4x all over x squared plus 1 squared. B. What if v is equal to 4t plus 3 to the negative 1 times 5t squared plus 3t minus 2? So my claim is that this is a quotient because negative 1 means that this factor is actually on the bottom. That v is equal to, since this is a positive one because they haven't written it, this is 5t squared plus 3t minus 2 to the 1 up top, and this is a negative 1, so that means that's 4t plus 3 on the bottom. That's all that represents. So we still have our f on top, we still have our g on bottom, and then so that's really the, that's a quotient. So we know that v prime is going to be equal to f prime g minus f g prime all over g squared. So the derivative of the top is going to be 10t plus 3 times the bottom, which is 4t plus 3, minus the top, which is 5t squared plus 3t minus 2, times the derivative of the bottom, which is 4, all over the bottom squared. Remember, there's no need to square that denominator. Just leave it alone. So now when we multiply these things together, I'm just going to FOIL the top. So I have 40t squared, that's here. This is going to be, I have 30t plus 12t is going to be 42t. Then last is going to be plus 9, so outside, inside, last. Now I'm gonna do this step in one. This gives you a 20t squared, but it's going to change its sign, so a minus 20t squared. this is going to give us a positive 12t, but this negative sign is going to change into a negative 12t. And this is going to give us a negative 8, but this negative is going to turn into a positive 8. All over that denominator squared. Combining all these like terms, 40 minus 20 is going to be 20t squared. These are like terms, so I'm going to have 30t. Last I'm going to have plus 17. All over 4t plus 3, 20 squared. Okay. Let's see. What if y is equal to e to the minus x? I should silence these before I do them, but it's not the first time. Okay, so what we're trying to do is I'm trying to make sure that you guys understand that that these negative exponents mean that we have a denominator here. So this is the same thing as 1 over e to the x. So really what I have is I have a rational that the top is f and the bottom is g, where the numerator is just that constant 1. So it means y prime is going to be equal to f prime g minus fg prime all over g squared. So we're going to get the derivative of the top. Well, the derivative of a constant is 0 times the bottom, which really doesn't matter because it's a 0 and that is a coefficient, minus the top, which is 1, times the derivative of the bottom. The derivative of e to the x is e to the x, all over the bottom squared, which is e to the x squared. Oh. So that means that's a 0, so this is minus e to the x on top, and the bottom is I would like you guys to know this, that when you raise powers to powers, this power to this power, this really is e to the 2x. But sometimes if you write it as e to the 2x, you might not see that that there's an e to the x down here, and there are two e to the x's here. So notice how they have the same base. They have the same base as e. So in order to divide, and the negative is going to come out front. In order to divide, you keep the base and you subtract the exponents. So the first exponent is an x, and then you're going to subtract the 2x. So this is minus e to the x minus 2x, which is going to be negative x. And again, negative x means it's on the bottom, so this is minus 1 over e to the x. All right. So I know technically I've already used these rules in previous examples, so this is my fault to put it in now, but I'm just going to formalize this. So power rule for negative integers. Technically this works for, why they force it to be integers. This works for all real numbers except when x is equal to -1. Is that right? Let's see. I'm trying to remember where that's... No, this just works for all real numbers. So negative integers. Okay. And x not allowed to be 0. Alright, so the derivative with respect to x of x to the n is equal to n times x to the n minus 1. So it's the same as before. Technically it works for all n's, so it's not really limited to integers, but most of what we work with are integers for right now. But I'll even show you one where it's a radical. So so finding derivatives. So example, determine the derivative. We've already done one like this, but we're going to do it again. So a, y is equal to 1 over x. So there's two different ways you can do this. You can use the quotient rule. So the derivative of the top. So let's kind of do that just to. So this is f over g, and then what I'm going to do is I'm going to use that power rule just to verify that this is the case. So that means y prime would be equal to f prime g minus f g prime all over g squared. So the top, the derivative of 1 is 0 times g, which would be x, minus f, which is 1, times the derivative of x, which would be equal to 1, all over the bottom, which would be equal to x squared. So what we get is we get negative 1 over x squared. Now we're going to do an a again, but we're going to do it using the power rule, so 1 over x. Well, 1 over x is the same thing as x to the negative 1. So that means y prime is going to be equal to that negative 1 is going to go in front, and that power is going to reduce by 1. So this is the same thing as negative 1 over x squared. So just to show you that power rule still works, even if the power is negative. So b, if I want y is equal to 5 over x to the fourth, well, you know you can handle that using the quotient rule. But the power rule is so much quicker. Now, this if I had something different up top, we'd have to be a little bit careful. If this was like a 5 e to the x up top over x to the fourth, and then we would have to use the quotient rule. But since I can write this as essentially like a power function, coefficient-based variable, then you know that you can use the power rule. It's got to be of essentially this form, of just a constant times x to the n. Because the reason why a constant times x to the n is because you can always pull out the 5 and just take the derivative of x to the minus 4. So y prime is going to be minus 4 times 5, which is minus 20. X reduce it by 1, so this is minus 20 over x to the fifth. I'm going to do it for a radical as well. What if y is equal to 3 root x? Technically, this works for all powers. Well, what we know is that 3 root x is 3 times x to the 1/2. So we can do the power rule just like this. So y prime is going to be 1/2 times 3, so 3/2. X to the, remember we're going to reduce it by 1, right? We're going to take 1 away from that. So reducing 1/2 by 1 is going to give you negative 1/2. So 3/2 x to the negative 1/2, which means that you have 3 over 2x to the 1/2, because that means the 1/2 is on the bottom, or 3 over 2 root x. Last thing, high order derivatives. So we can have first, second, third, fourth, so on derivatives. So our high order derivatives. So we know that dy dx represents the first derivative. Now the derivative with respect to x of dy dx, which would be the derivative of the derivative, is going to be the second derivative with respect to y. Notice how there's 2 d's and 1 y, and over here there's 2 dx's. That's why we have that notation with the 2 here and the 2 here. This is going to be equal to y double prime. Now the derivative of this, so the derivative with respect to x of this previous thing, derivative with respect to x of the derivative of y with respect to x. Remember that the derivative is just d dx. That's why we're going to have 3 d's, and then 3 dx's is going to be equal to the third derivative. And then so on. So when we get beyond 3, actually let's do the next one. So the derivative with respect to x of the derivative with respect to x of the derivative with respect to x of this derivative of y with respect to x is going to be d4 dy dx4 is going to be the fourth derivative. So we tend to put like a 4 in parentheses there. The reason why we do a 4 in parentheses is because this is not y to the fourth, this is the fourth derivative. So then, of course, we can keep going. So beyond this, you're just going to use those parentheses notations. Yep. All right, so example. Determine the first, second, third, fourth, fifth, and so on derivative. So A. So, well, I'm just going to say f of x, which is equal to 5x to the fourth minus 7x cubed plus x squared minus 8x plus 1. So if this is equal to y, then y prime, which would be equal to f prime of x, which is going to be the derivative with respect to x of this expression. I'm not going to write this, I'm just going to start doing them from now on. So the derivative of this thing is going to be equal to 20x cubed minus 21x squared plus 2x minus 8. Now, y double prime, which is going to be equal to f double prime of x, is going to be equal to the derivative of this new function. Got messy. Well, the derivative of that function is going to be 60x squared minus 42x plus 2. The third derivative is going to be f triple prime of x, which is going to be equal to the derivative of the second derivative, 60x squared minus 42x plus 2. So this is going to be equal to 120x minus 42. Okay, I'm not going to keep writing that notation. So the fourth derivative is going to be equal to, the derivative of this thing is going to be 120. The fifth derivative is going to be equal to, so 120, my bad, it's not 120x, it's 120, because the 1 is going to turn into a 0, right? 120x to the 0, so this is equal to 120. And the derivative of a constant equals to 0. And what you'll notice is beyond this, like the sixth derivative and so on, is all going. These are all just going to be zeros, because the derivative of a constant is a constant, and the derivative of and so on. The derivative of a constant is 0, and since this is a constant, the derivative of that constant is still 0. So these are all just going to be zeros from now on. So what you'll notice with polynomials is they'll eventually annihilate down to 0 if you take enough derivatives. The question is, how many derivatives did it take? How many times did you have to take the derivative before this fourth degree turned into 0? And you'll notice it's one more passes through.